A star's distance is literally time travel. Light years tell us how far light travels in 1 year. That short definition explains why astronomers call distances in years. The idea matters because light carries a record of its past. Scientists read that record like pages in a book. Definition then becomes practical because we measure distance as elapsed light travel. Scientists use that measure to see objects as they were. The stakes are obvious because this affects our sense of cosmic history. Mechanically, a light year equals about 9.5 trillion kilometers, measured by light speed times time. Light speed acts as a ruler, while time gives it scale. An example is Proxima Centauri, 4.24 light-years away, where we see the star as it was 4 years ago. Another example is Andromeda, at about 2.5 million light-years, visible as ancient light. Quick mental image: imagine reading yesterday's newspaper instead of today's sky. The anchor is simple: light years convert time into distance, giving us a cosmic timeline. A light year is distance measured by light travel over time. This matters because distance and time are linked by light speed. Mechanically, we multiply the speed of light by 1 Julian year to get the length. That gives roughly 9.5 times 10 to the 12th kilometers. Scientists use that single rule across scales, from nearby stars to distant galaxies. For example, Proxima Centauri at 4.24 light-years appears 4 years in the past. Another concrete case is Alpha Centauri A and B, about 4.37 light-years, where signals take 4 years to arrive. Quick mental image: think of light as a slow-moving tape, storing older scenes at greater distances. The stakes are practical because observational astronomy reads time-encoded light to reconstruct events. Mechanism detail then matters, as the speed of light is a universal constant, and it becomes our standard ruler. Observationally, astronomers calibrate instruments in light years because it links directly to observable delays. A one-sentence recap: a light year turns light's travel time into a measurable distance. Astronomers prefer light years for clear practical reasons. Using light years ties observation directly to time, which observers measure naturally. Mechanically, light years let astronomers say how old the light is without converting units constantly. Instruments record photons that traveled long distances, and time stamps on arrival tell us the delay. That delay matters because it reveals cosmic history, such as star formation epochs. For example, when we observe a galaxy 10 billion light-years away, we see it as it was 10 billion years ago. Another clear case is the Hubble Ultra Deep Field, where each faint dot is ancient light, billions of years old. Quick mental image: peer through a time-lapse camera that looks across the universe. The stakes include understanding galaxy evolution and reconstructing the universe's timeline. The anchor is straightforward: light years make cosmic time visible and comparable. Parallax gives a direct geometric measure for nearby stars. The method matters because it requires no assumptions about intrinsic brightness. Mechanically, astronomers record a star's apparent position at opposite points in Earth's orbit, then measure the tiny shift. That angular shift relates to distance by simple trigonometry, because baseline and angle define a triangle. For example, the European Gaia mission measures parallax for over 1 billion stars with micro-arcsecond precision. Another concrete example is the classic measurement of Barnard's star, whose large parallax showed it is very close. Quick mental image: hold your finger at arm's length, then alternate closing each eye and notice a small jump. The stakes are calibration because parallax anchors the next rungs of the cosmic distance ladder. One-sentence recap: parallax gives the first, reliable distances using geometry alone. Observers then apply the inverse square law, turning brightness difference into distance in light years. A concrete example is Edwin Hubble's use of Cepheids in the Andromeda Nebula, which proved it was a separate galaxy. Another modern example is Cepheids in the Large Magellanic Cloud, used to calibrate further distance indicators. Quick mental image: picture a lighthouse whose flash rate tells you its true wattage. The stakes are huge because Cepheids set the scale for far more distant measurements. Final recap: Cepheid variables translate pulsation into absolute distance across the galaxy and beyond. Type Ia supernovae serve as bright standard candles for distant galaxies. Their stake lies in reaching distances beyond Cepheid usefulness. Mechanically, these explosions reach nearly uniform peak luminosities, and that uniformity allows distance estimates. Astronomers measure peak brightness, then compare it to expected absolute brightness to compute distance. A concrete example is the discovery of cosmic acceleration based on distant Type Ia supernova measurements. Another example is using nearby Type Ia events to cross-check Cepheid distances in the same host galaxies. Quick mental image: imagine identical flashbulbs fired at different distances, where brightness difference reveals range. The stakes are profound because these distances feed into measurements of the universe's expansion rate. Anchor: Type Ia supernovae extend our light-year ruler deep into the cosmos. Redshift measures how much wavelength stretches as the universe expands. This concept matters because more distant light arrives more redshifted and older. Mechanically, astronomers measure spectral lines, then compute how much those lines shifted toward red. That shift converts into a recession speed, using well-established physics, which then links to distance through cosmological models. For example, Hubble's original measurements showed a proportional relation between redshift and distance, leading to the Hubble law. A concrete modern case is measuring redshifts across galaxy surveys to map large-scale structure. Quick mental image: imagine sound waves stretched by a receding siren, but for light instead. The stakes include measuring the expansion history and constraining dark energy properties. One-sentence recap: redshift provides a scalable link between light travel time and cosmic distance. People often confuse light travel time with object age. The distinction matters because a distant galaxy's light is old, but the galaxy may still exist differently now. Mechanically, light travel time is purely observational delay, while age refers to intrinsic formation time. Another confusion is mixing units, such as parsecs and light years, which astronomers convert routinely. For example, 1 parsec equals about 3.26 light years, used commonly in parallax studies. Another practical limit is dust extinction, which makes objects appear dimmer, skewing naive distance guesses. Quick mental image: imagine a foggy night where distant lights dim and redden. The stakes are correction, calibration, and careful cross-checking among multiple indicators. The anchor is clear: light years are powerful, but require context and calibration to yield accurate distances. Remember the opening payoff: a light year turns time into spatial distance. That fact lets astronomers read the universe's history directly from observed light. If you liked this explanation, consider exploring one detailed method next, such as parallax or redshift. A gentle next step is checking measured examples like Proxima Centauri and Andromeda to feel the scale. Thank you for listening, and enjoy watching the sky with a new sense of time.